Welcome. I'm Professor George Easton, and this is the first of a series of videos on measurement system evaluation. This is part one, and in part one I'm going to give an overview and some context and an introduction to the key and most basic ideas. I wanted to point out that measurement system evaluation is also sometimes called measurement system analysis, and I will use these two terms essentially interchangeably. Now, measurement is absolutely key and central and critical in Six Sigma. In fact, the emphasis on metrics is one of the things that distinguishes Six Sigma from quality management systems that came before. In Six Sigma, measurement is pervasive. Part of the philosophy of Six Sigma is that associated with every goal should be a metric that can be used to assess whether or not the goal is met. And this is not only for goal setting for individuals, but also for goal setting in terms of improvement projects, such as the kind of improvement that you would be trying to drive in a DMAIC project. So associated with every goal, whether it's for a person or for a team as part of a project, there should be a metric. Metrics are also very important for the voice of the customer. Important to understand customer satisfaction, but beyond customer satisfaction, important to understand needs and requirements of customers. Metrics obviously are essentially important to process management because it's metrics that feed into things like statistical process control used to control processes and to ultimately eliminate special causes and make process capable. Metrics are important in supplier assessment and management and in the qualification of supplier systems, making sure that suppliers' systems can in fact produce capably and within the specifications. Metrics are important in the human resources area. They're important for understanding employee satisfaction, for measuring employee effectiveness, for example, through training, and so on. Metrics are a key part of benchmarking. One of the key things that people do in benchmarking is to determine what metrics and what levels of those metrics correspond with world-class performance. And finally, metrics are central in experimentation. And this is whether it's experimentation in new product development or experimentation in process improvement or experimentation in characterizing processes to really understand how their control variables relate to their outcome. So metrics really are central throughout Six Sigma. Now, wherever there's a metric, there's a measuring instrument. And I'm going to use the term measuring instrument here very loosely because I want it to include the kinds of measurements that are often done by human beings. And in many cases, measuring in organizations involves a human being and a human perception in assessing the measurement. So, for example, a human being and their judgment and perception are often used to determine whether the color of a product is within specification or whether a surface is flat enough or smooth enough or a lot of those kinds of things. But when a human being is making the judgment, then the human is a measuring instrument. Of course, in many other cases, the measuring instrument really is an instrument. It's a device, like a weigh scale or a stopwatch or some other device that we use to measure things. So by measuring instrument, I can mean both. Whatever it is that is generating the assessment is the measurement instrument. Now, there are really two key ideas that are the most fundamental in measurement system evaluation. The first is that the measurement must be on target, which is to say that there must be little or no bias. And so being on target, what that means is that the average value you get from the measuring instrument ought to be aligned with equal to the characteristic that you're measuring. The second idea, though, has to do with variability, and this is a more difficult idea because it's very easy for us to tend to think that there's little or no variability in things. But the second idea is that the variability of the measuring instrument must be small enough that you can reliably detect differences in the characteristic that you are focusing on, the thing that's being measured. So those are really the two key ideas. You've got to be on target, and you've got to be sufficiently precise that you can see what you need to see. Measurement variation does matter. Being on target obviously matters. I think that's common sense. But variation matters as well. And we have equations that can help us understand exactly how variation in the measurement system matters. This equation shows that the variance of the thing that you observe, so obs here means the observed metric, this would be the variance of the data points you are, for example, plotting on a chart of individuals. That's going to be the sum of two parts. The first part is the variance of the characteristic that you're measuring. So I'm using real here to indicate the real characteristic, the real number that you wish you had. That number has a variation, and so this is going to be the variance of the characteristic. Then you add to that the variance of the measuring instrument. So MEAS here stands for measure, and it's going to be the error in the measurement and the variance of the error in the measurement. And as in statistics generally, what adds here are variances. So we get the variance of the thing we're observing is the sum of the the variance of the number that we get is going to be the variance of the characteristic that we care about plus the variance of the measuring instrument. And we, of course, can rewrite this in terms of standard deviations because variances in general are difficult to interpret. And when we take the square root of both sides, we get that the standard deviation that we observe, the number that we're going to plot on that chart for individuals, it's going to be the square root of the sum of the variances, where the first variance is the variance of the characteristic that we care about, and the second is the variance of our measuring instrument. So you can see that if your measuring instrument has the same variance as your actual characteristic, then what's under the square root here is going to be 2 times that variance. And when we factor out the 2, we get the square root of 2. And so what that means, if the variance of my measurement instrument matches the variance of the thing that I'm measuring, then the variance of the standard deviation, rather, of the numbers that I'm plotting are about 1.4 times the standard deviation of that characteristic. So measurement variation can matter if it's large, and it can matter in very important ways. Now, there's a rule of thumb with respect to the variation in measurement that is very central in understanding what we're going to do later in terms of trying to assess whether or not a measuring instrument is sufficiently precise. The rule of thumb is that the standard deviation of the measuring instrument should be 10% or less of the standard deviation of the characteristic that you are measuring. And so we can put this into an equation. What it says is the standard deviation of the measuring instrument divided by the standard deviation of the thing that you're measuring ought to be less than or equal to 10%. Now, having said that, this is basically a criterion for how precise the measurement instrument is. I want to review a couple of things that I've classified here as how to think. And I classify things as how to think sometimes when the habits of thinking that people bring to the topic are often different than the perspective that's taken within Six Sigma. So the first thing under how to think is that all measuring instruments produce variation, and this variation is big enough to care about. Okay, it matters. Okay, so like other processes, measuring processes produce variation. You should not look at measurement as though it's not a variation-producing process. The second thing is that many measurement instruments that are deployed and in use are not capable. They're not qualified. So by capable or qualified, I mean capable means that the standard deviation of the measuring instrument is 10% or less of the standard deviation of the thing that you are measuring. And when you look at studies done to assess whether or not measuring instruments actually do have a small enough standard deviation, you frequently find that at least half the time, or even more than that, they aren't. Okay, they are too variable to effectively measure the thing that you care about. So I want to note here that measurement itself is a process, and that to be an effective process, measurement needs to be well defined. So the measurement process then should be defined by the 5 W's and the 1 H, which is a very useful mnemonic for defining things. So the 5 W's are who's going to take the measurement, what they're going to measure, when they're going to measure it, where it's going to be measured, why they're doing it, and perhaps the most important one is how that measurement is to be taken. The measurement system should also be calibrated, and I'm going to return to calibration later, but it's basically the idea that the measurement process has to be set on target, and it has to be done periodically because measurement systems tend to drift, so it needs to be calibrated. It needs to be in control. If the measurement system itself is not in control, then it's not predictable. And then finally, it needs to be capable. And the idea here of capability of the measurement system is that the standard deviation of the measuring device is less than 10% of the standard deviation of the thing that you are measuring. All of this should be found in the process control plan. So it's the control plan that typically specifies what's going to be measured, how it's going to be measured, who's going to be measuring it, and how you analyze those metrics as well. Now I want to return very quickly to terminology for the kind of thing that we're talking about doing here, largely because I need to introduce this first term to you, Gage R&R, which stands for Gauge Repeatability and Reproducibility. In the next video, I'm going to define these terms, but all three terms that we've now run into all refer to essentially the same thing. If somebody talks about Gage R&R or Measurement System Evaluation, MSE, or Measurement System Analysis, MSA, they're talking about the same thing, which is determining that the measurement system being used, or the measurement instrument, is both on target and of sufficiently small variation that it is really useful for what you're trying to measure. Now I want to take a very quick aside here and talk about this word gauge. It turns out that there are two correct spellings of the word gauge. One of them has a U in it and the other one does not. And both of these really are correct if you go look them up in the dictionary. The spelling of gauge that uses the U is the most common spelling that people use in practice, in real life, I should say common life. So chances are most of the time that you've seen the word gauge spelled, you've seen it spelled with a U. However, gauge spelled without the U is the most common spelling in technical contexts. For example, in engineering and in statistical process control and so on. So if that looks a little weird to you, it isn't wrong. And in fact, it's the spelling that is most common in this area and the spelling that I'm going to use going forward. So in summary then, in this introduction, I've presented the most basic, sort of biggest ideas that have to do with measurement system evaluation. The first one is that the measuring instrument needs to be on target on average. That's the idea of bias. And the second one, which is more complicated for people, is that the measuring instrument needs to be precise enough that you can reasonably see differences or changes in the characteristic that you're trying to measure. And the criterion for that, the rule of thumb criterion, is that the standard deviation of the measuring instrument needs to be 10% or less of the standard deviation of the thing that you are measuring. So these are the big ideas. And in the second part of this video series, we're going to begin to get a little bit more specific, and I'm going to present some of the more detailed basic ideas and terminology.